So today we will be talking about a new chapter of NCERT Class 11 book, which is States of Matter. So what are the objectives of this chapter? So it will explain the existence of different states of matter in terms of balance between intermolecular forces and thermal energy of particles. So after reading this, you will come to know about what are the different states of matter and how they exist, okay? And what are the various intermolecular forces and thermal energy of particles. It will also explain the laws governing behavior of idle gases and apply gas laws in various real life situations. Explain the behavior of real gas. So this chapter will deal with all the laws of the real gases and behavior of the real gases. So there are two types of gases: ideal gas, which behaves like an inert gas, and real gas, which exactly is just opposite to that of ideal gases. It will describe the condition required for the liquefaction of gases and also realize that there is continuity in gaseous and liquid state. It will differentiate between gaseous states and vapors. So until now, many of you might think that gaseous state and vapors are same, but it will this chapter, after reading this chapter, you will get to know the answer that gaseous states and vapors are different, and they are different in what ways that will be learned from this chapter. And this chapter will also explain the properties of liquids in terms of intermolecular attraction. Actually, all these states of matter will be dealt with intermolecular attractions between the particles only. So, in the introduction, so in previous units, we have learned about the properties related to single particle of matter. So, before this, when we read about the periodic properties, there also we learned about atomic size, atomic radius. We talked about ionization enthalpy. We talked about the electron gain enthalpy, electronegativity. So all of these particles, all of these properties were properties of that was related to single particle of matter. So before this chapter, we were talking about all the properties of the single particle of matter. But in this chapter, we are not going to do that. We are going to study the properties of the bulk. So by bulk, what does that mean? So most of the observable characteristics of chemical systems with which we are familiar represent bulk properties. For example, that is the properties associated with the collection of large number of atoms. So instead of talking about a particular atom, instead of talking about the properties of a particular atom, we will talk about the properties of the bulk, like large number of atoms in total. Okay, large number of atoms, ions, molecules, whatsoever. So, for example, an individual molecule of liquid does not boil, but the bulk boil. So, when you have water in the pan and you heat it to 100 degrees centigrade, then what do you expect? So, what do you see basically? You see the whole water is boiling. So, it is the bulk. All the atoms of the bottle starts boiling. It is not that a single atom of that water of the whole water in the pan will boil. No, it is a bulk property. So, boiling is a bulk property. Okay. So whole of that starts, all of the atoms of the water starts, or I can say whole of the molecules of water starts boiling and not a single molecule. So that is bulk property, and also selection of water molecules have wetting property and not a individual molecule wet. Water can exist as ice, which is solid. It can exist as liquid, or it can exist in the gaseous state as water vapor or steam. This we all know, right? So physical properties of ice, water, and steam are very, very different, and that is why they have different states, because the physical property needs to be different. We know that ice is solid, liquid, water is liquid, and steam is gas. So in all these three states of matter, so all of these are called the states of matter. But the chemical composition in all of the three states are same. Although the physical properties of all these states are different, but their chemical composition is water only. So when you're talking about ice, you're talking about H2O molecules only. When you are talking about water, liquid, it is the same thing, H2O molecules only. And when we are talking about water vapor, it is nothing but the H2O molecules only. So the chemical composition of the water is not going to change. It will be always H2O. It is not going to become H3O in different state, H4O in different state. No, the chemical composition remains the same, though the physical properties changes in different states of matter. Characteristics of the three states of water depends on the energies of molecules and on the manner in which the water molecule aggregates. Same is true for other substances also. Here we are talking just about water, but it is also for other substances which exist in different states of matter. So chemical properties of a substance do not change with the change in its physical state. This is so true. We just read it. So the chemical composition is not changing, hence chemical property will not change. So the physical property changes with states. But rare of chemical reactions do depend upon the physical state. Some of the chemical reaction, the rate of the chemical reaction changes when you have different physical states. So many times in calculations, while dealing with data of experiments, we require knowledge of the state of matter. So when you write an equation, a very, very simple equation, so you need to mention the state in which that compound is you are taking. Okay, supposingly you are taking A, and B, and you're getting C in the reaction, then you must know what are the states of A and B, and when you get C, what is the state of C. Therefore, it becomes necessary for a chemist to know the physical laws which govern the behavior of matter in different states. So in this unit, we will learn more about these three physical states of matter, but particularly liquid and gaseous states. To begin with, it is necessary to understand the nature of the intermolecular forces, molecular interactions, and effect of thermal energy on the motion of particles, because the balance between these determines the state of substance. So this line is very important. So these are the three terms, that the intermolecular forces, molecular interactions, and effect of thermal energy on the motion of particles. So basically, these three properties will govern that your substance will be in which state. Okay. So first, let us understand all these three properties in details. So let us take first the intermolecular forces. So what is intermolecular forces? By term, we can correlate, right? So it is some force that is acting between the molecules, right? Not inside the molecule, but between two molecules, between more than two or more than two molecules. Okay. So these are the forces of attraction, intermolecular forces. So by this term, you cannot exactly state that it is for attraction or repulsion. It can be both. Forces can be both attractive and repulsive at the same time. So intermolecular forces are the forces of attraction and repulsion between the interacting particles, that is atoms or molecules. So this term does not include the electrostatic forces that exist between two oppositely charged ions and forces that hold atoms of the molecule together, that is the covalent bond. So here we are not talking about the exact bonds between the atoms. No, and also we are not talking about the electrostatic forces that exist between two oppositely charged entities. Here we are talking about intermolecular forces that exist between any greater than one atoms or molecules. Or let me say it, neutral atoms and molecules. These are not the exact bonds. Okay, and these are not the electrostatic forces as well. These are something different. This can be attractive, this can be repulsive between two or more atoms and molecules. So attractive intermolecular forces are known as the van der Waals forces. And in honor of Dutch scientist Jonas van der Waals, 1837 to 1923, who explained the deviation of real gases from the ideal gas behavior through the forces. So we will, after knowing these terms, we will also get to this chapter, because these terms are very, very important in this chapter. So when you will understand these terms, then this chapter becomes very easy. Okay, so all those attractive intermolecular forces are termed as van der Waals forces. So we will learn about this later in the unit. Van der Waals forces vary considerably in magnitude and include dispersion forces or London forces, dipole-dipole forces, and dipole-induced dipole forces. A particularly strong type of dipole-dipole interaction is hydrogen bonding. Only a few elements can participate in hydrogen bonding, therefore it is treated as a separate category. So various other types of van der Waals forces. So van der Waals force is an attractive force, attractive intermolecular forces, and there are different types of van der Waals forces that may exist between atoms and molecules. These are dispersion forces, or that is also called London forces, dipole forces, that is between two dipoles, and dipole induced dipole forces, and another type of dipole-dipole interaction is hydrogen bonding, which we are not going to study in van der Waals forces, and because all the elements doesn't show hydrogen bonding interaction. Okay, so so let us start. So at this point, it is important to note that attractive force between an ion and a dipole are known as ion dipole forces, and these are not van der Waals forces. I already told you. So here, whatever we are talking about, we are not talking about ions. We are talking about neutral atoms and molecules. So any forces between an ion or dipole or ion and ion, it will not be dealt in the intermolecular forces. So we will be dealing with different types of van der Waals forces in the next subsequent units. So let us start with the dispersion forces or London forces. Dispersion forces and or London forces. Okay. Atoms and non-polar molecules are electrically symmetrical and have no dipole moment. So when we are talking about just single atoms, which again is not connected with any other atom, so that no bonds with any other atom, and that is why it is called atom. Okay, so 2 and 3 atoms that are bonded, they are called molecules. So atom is electrically neutral, and also the charge density is also symmetrical, so it will have no dipole moment. And same with non-polar molecule. It will be also electrically symmetrical and hence no dipole moment. So because the electronic charge cloud is symmetrically distributed, so there is no dipole moment. But a dipole may develop momentarily, such even in such atoms and molecules. This can be understood as follows. So in order to have some attractive forces, because van der Waals are only attractive forces, so we are dealing with all the attractive forces that exist between atoms and molecules. So in order to have any kind of attractive forces, or let's say in a broader term, in order to have any kind of forces, you need to have some momentarily like dipole. Okay, so that means if you have symmetrical charge distribution, there is no dipole, there will be no force. So in order to have some force, you need to have a little bit, or for that just that time period, you need to have some momentarily developed dipole. So let us understand what that is. Suppose we have two atoms A and B in a close vicinity to each other. And obviously, in order to have such forces, these forces are not that much strong. So your atoms or molecules that are having these such forces needs to be in close vicinity. So suppose we have two atoms A and B in the close vicinity of each other. Figure 5.1a. Okay, so this is also looking symmetrically neutral. This is also looking neutral. This is also neutral. All these there is symmetrical distribution of the electron charge cloud. Okay, it may so happen that momentarily electronic charge distribution in one of the atoms, say A, becomes unsymmetrical. That is, the charge cloud is more on one side than the other. Okay, so for some period of time, this has become, atom A has become, it was having symmetric electronic charge distribution. For some time, it is now having, for a particular time T, it is having unsymmetrical distribution of electronic charge. Okay, so if B is in close vicinity with A, then this unsymmetrical electronic charge distribution will induce dipole to B. So if positive charge is more on the left side and here is the negative charge, then positive in atom B, positive charge will be developed in such a way that will cause attractive forces, and negative charge will, so basically dipole will induce, due to which there will be some positive or say attractive forces. So that force we are talking about is nothing but the dispersion forces or London forces. Okay, so this results in the development of instantaneous dipole on atom A for a very short time. And this instantaneous or transient dipole distorts the electron density of the other atom B which is close to it, and as a consequence, a dipole is induced in atom B. So we were talking about this only. The temporary dipoles of atom A and B attracts each other. Now, similarly, temporary dipoles are induced in molecules also. So this force of attraction was first proposed by German physicist Fritz London, and that is by the name London forces. And for this reason, force of attraction between two temporary dipoles is known as London forces. Other name for this force is dispersion forces. These forces are always attractive, and interaction energy is inversely proportional to the sixth power of the distance between the two interacting particles. Okay, so these forces highly depends upon the distance. You have to have the atoms in order to have such forces, London forces, or say van der Waals forces. You have to have the atoms or molecules in close vicinity. If you have the atoms and molecules far apart, then these forces doesn't exist. Okay, so the force of attraction is inversely proportional. So if inversely proportional to sixth power of the distance between two interacting particles. So these forces are important only at shorter distance. So if the distance between two molecules r is very small, and to the power of 6 is inversely proportional, okay, to the forces. So force is inversely proportional to the sixth power of the distance between two atoms or molecules. See how much distance governed these forces are. So it is not 3 to 6. Okay. So let us talk about another type of forces, that is another kind of van der Waals forces, that is the dipole-dipole. So by the name you know that you're not talking about symmetrical molecules here. So you are talking about those molecules which have unsymmetrical electron distribution. So that is why it will have both the molecules having these forces will have permanent dipoles, and that is why the interaction. Okay. Dipole-dipole forces acts between molecules possessing permanent dipoles. Ends of the dipole possesses partial charges, and these charges are shown by the Greek letter delta. Partial charges are always less than the unit electronic charges. The polar molecules interact with neighboring molecules. Figure 5.2a shows electron cloud distribution in the dipole HCl, and figure 5.2b shows dipole-dipole interaction between two HCl molecules. So this molecule is not symmetrical. The electron distribution of this molecule is not symmetrical. There exists some delta positive and delta negative charges on the atoms, and due to which, if you have considered two atoms of such two molecules of such entity, like two HCl molecules, then you have to draw it in such a way to have lesser energy. So in order to do so, you will have delta negative here, and the delta positive will be towards delta negative in order to have the attractive forces. So this molecule has a permanent dipole, and these two molecules has this attractive forces. Again, the dipole-dipole interaction energy between the stationary polar molecules is proportional to 1 upon r to the power of 3. That between rotating polar molecule is proportional to 1 to the power of r, 1 upon r to the power of 6, where r is the distance between the polar molecule. So when you have stationary polar molecules, then you have a greater repulsion. Okay. So but when you have rotating polar molecules, then you don't. Then you have the forces is directly proportional to 1 upon r to the power of 6. In that case, distance matters quite a lot. So besides dipole-dipole interaction, polar molecules can interact by London forces also. So thus cumulative effect is that the total intermolecular forces in polar molecules increases. So non-polar molecules will only have London forces, and polar molecules will have dipole-dipole forces as well as London forces. Okay. Now, third type of van der Waals force is the dipole-induced dipole. So that is, we are talking about two different molecules. One will have permanent dipole, another molecule will not have permanent dipole, but because of the close vicinity between these two different types of molecules, the polar molecule or the molecule that has the permanent dipole will induce the dipole in the neighboring atom which has symmetrical electronic charge density. So this is a non-polar molecule. This is a permanent dipole molecule. So when this will come in close proximity, so here it is delta negative. So it will induce the electronic charge in such a way that it will have positive or attractive forces, attractive interaction. So for that to happen, it will have delta positive this side and delta negative this side. That is why it will have now attractive forces. So this has also, this can be seen from here. So dipole-induced dipole forces, let us see what is written in the book. So this type of attractive forces operate between the polar molecule having permanent dipole and the molecules lacking permanent dipole, that is a non-polar molecule. So the permanent dipole of the polar molecule induces dipole on the electrically neutral molecule by deforming its electron cloud. I already told you. Thus, an induced dipole is developed on the other molecule. In this case also, the interaction energy is proportional to 1 upon r to the power of 6. So these all things you need to learn, like which type of forces. In case of van der Waals also, we see that it is directly proportional to 1 upon r to the power of 6. In case of dipole forces, we saw there are two types. If we are talking about the stationary atoms or molecules, then the force is directly proportional to 1 upon r to the power of 3. And when we are talking about rotating dipole molecules and interaction between such rotating dipole molecules, then the force is directly proportional to 1 upon r to the power of 6. Again, for dipole-induced dipole forces also, we have forces directly proportional to 1 to the power of 1 upon r to the power of 6, where r is the distance between two molecules. Now, induced dipole moment depends upon the dipole moment present in the permanent dipole and the polarizability of the electronically neutral molecule. So here it will be delta positive or delta negative will depend upon the permanent dipole moment of the molecule. So we have already learned that molecules of larger size can be easily polarized. Okay, so let me explain this. When you have large molecule, then that means you have large orbitals, and large orbitals, in that case, you have electrons, they are very much dispersed, and that is why in that case you can easily polarize the large molecules, okay, because the orbitals are dispersed. High polarizability increases the strength of attractive interaction. So in this case also, cumulative effect of dispersion forces and dipole-induced dipole interaction exists. Again, this is a cumulative effect of dispersion forces and dipole-induced dipoles. So dispersion forces are everywhere. Okay. Now we are talking about the van der Waals hydrogen bond. So it is not considered. Yeah, it is also one kind of van der Waals forces only because it is attractive force, but it is not. Before this, whatever we studied the dispersive forces, we studied the dipole-dipole interactions, we also studied the dipole-induced dipole forces also. All of those forces were applicable for all the molecules or elements, but for hydrogen bond, it is not applicable for all the elements and molecules because it is only applicable for certain. For hydrogen bond, hydrogen must be there, right? And also hydrogen is electropositive in nature. So in order to have such interaction, it only shows hydrogen bonding. Is actually kind of strong interaction, and hydrogen only shows hydrogen bonding with very, very much highly electronegative elements, and those are fluorine, nitrogen, and oxygen. Only these two. Okay, sorry, these three. So let us read. So this is a special case of dipole-dipole interaction. Again, it is a type of dipole-dipole only. So hydrogen is electropositive, so it has delta positive charge. And this hydrogen, and this is the hydrogen bonding interaction, and there has to be some electronegative atom element that will have delta negative, and this hydrogen should also be with such a molecule that it will have some delta positive charge. So will this hydrogen have delta positive charge when it is connected with hydrogen? No, it has to be connected with some another molecule that is electronegative than hydrogen, and that is how only it can have some delta positive charge, and only it can form hydrogen bonding with three elements F, O, and N. That is fluorine, oxygen, and nitrogen. Okay. So uh, we have learned about okay. This is found in molecules in which highly polar NH, OH, and HF bonds are present. I already told you that. Sorry, I had lost connection. I already told you it is found. It is found in N, O, and F types of molecules, elements only. If these three types of elements are present and electropositive hydrogen is present, then only, and it should be in close proximity. So all of these three things, and then only you will have, or you will see hydrogen bonding. Although hydrogen bonding is regarded as being limited to FON, but species such as CF minus may also participate in hydrogen bonding. This is also seen sometimes and not always. Energy of hydrogen bond varies between 10 to 100 kilojoule per mole. This is quite significant, okay? Amount of energy. Therefore, hydrogen bonds are powerful forces in determining the structure and properties of many compounds, and for example, proteins and nucleic acids. So, strength of hydrogen bond is determined by the Coulombic interaction between the lone pair electrons of the electronegative atom of one molecule and hydrogen atom of the other molecule. So, this is the diagram. So, this is H, it is delta positive, it is connected to F, and this is another HF, and here F is delta negative and delta positive. So, and also it has to be close to proximity, and you see very strong hydrogen bonding interaction. Intermolecular forces discussed so far are all attractive, but molecules also exert repulsive forces on one another. When two molecules are brought into close contact with each other, the repulsion between the electron clouds and that between the nuclei of two molecules comes into play. Okay, so when there are electrons close to each other of two molecules, then there will be repulsion, right? So magnitude of repulsion rises when rapidly as the distance separating a molecule decreases. Again, the same thing. If the distance between two molecules having electron cloud density towards each other decreases, then the repulsion will increase. Okay. So this is the reason that liquids and solids are hard to compress, because in that case you have atoms very close to each other, and if you further try to compress, like further try to make the atoms even closer to each other, then there we know that all the atoms above shield, all the atoms are shielded by various electrons. So nucleus is in the between, right? So if we try to compress solids and liquids that already has atoms very close to each other, and you try to decrease the distance between the atoms even closer, then there occurs repulsive forces, and that is why it is difficult to compress liquids and solids. So in these states, molecules are already in close contact, therefore they resist further compression, as that would result in increasing repulsive interactions. So this in this lecture, we will be talking about till here only, and from thermal energy we will be talking about in the next lectures. Thank you.